Good morning everyone, and welcome back to our channel and our course on CNC shift programming. In the last video we saw how to use the roughing macro for internal and external machining. I have to admit that I didn't really like that video because I struggled a bit to navigate between the whiteboard and the simulator. The explanations come out better on the whiteboard, but the only downside is that if you make a small typing error, you might not notice it. At this point, I want to thank everyone who occasionally points out, hey, you forgot a minus sign, because when I'm writing on the whiteboard, I sometimes make a mistake or a small error, especially when I'm thinking about what to say next. The simulator catches those mistakes, but the whiteboard doesn't. So basically we said that with ISO programming, meaning point to point, we can already do everything. Today let's focus on tapping, meaning we'll create a hole using a fixed drilling cycle with a pecking cycle, and we'll tap it. The hole is the one you see. I see it on the right, but maybe you'll see it on the left of your screen. Anyway, it's a 30mm long hole to be threaded M14, so we'll start with a pilot hole of 10.2. What exactly is it about? What does it mean when we talk about drilling with a pecking cycle and the related diameter, which is 10.4 facing 12, the pilot hole in 14, and 12.2 if I remember correctly. Earlier I mentioned 10.2, but there are tables that specify this. We need to focus on the programming. This hole is 30mm long. Drill bit. There are two options. Either position yourself in front of the piece, I move here, do it in one go and then pull back, or do it in one go, retract by a millimeter, do it again, retract by another millimeter. Obviously, this is to help you understand the tip won't be stepped, it will move in one direction back and forth. This is important for chip breaking, especially when we have materials like very pasty metals where the chip doesn't break and risks getting tangled around the tip or creating volume in the tip's helix and breaking it. Let's say, for example, we have a hole that's approximately 30 long and 12 in diameter. Nowadays those sharp coated tools don't cause problems, but we learn to manage them in this way. We have a flat tip and a low alloy material, so to drill a hole like this, we basically need to give it three parameters. A target Z, a break interval, meaning how often my tip goes in, stops, pulls back a bit, and then re-engages, and retraction, which is how much. I want to pull back. Yes, because for some materials, just stopping is enough to break the chip, while for others, it's better to pull back completely. So this is the macro for chip breaking. Some Fanuc machines have this as an option. They even have the ability to completely exit the piece and re-enter. Sometimes it's necessary, sometimes it's not. If the machine doesn't have it, you do it in ISO, make a pre-hole that's half the length, then exit and make the other hole. You also need to use your head a bit. So the three parameters are target Z, break interval, and retraction. Fanuc, how does it give it to you? Let's say we've named our tip TUO101 and we're working with a coidal tip that is programmed at X0. So what do we do? Let's set a G97, 700, M3. Remember, the drill bits spin in the opposite direction. Then G0, X0, Z4. We position ourselves here, safely. To the Arani, to the Arani, to the Arani, to the Arani. In some machines, the F needs to be set first, in macros, while others accept it, in the macro itself. Just to be safe, we set the feed rate F012 before giving the macro. Here comes G74, R1, G74, Z30, Q5000. What does that mean? R1, G, 74, Z minus, 30Q. We instruct the machine to tick in 2 blocks. Using G74, we execute a deep drilling cycle with a chip breaker. The macro ends at Z30, moving from Z4 to Z30 in 5,000 thousandths. Every 5 millimeters, you stop, retract 1 millimeter, and restart. If travel isn't a multiple of 5, the last step can vary. Starting from Z4, steps are Z1, Z6, Z11, Z16, Z21, Z26, Z30. Begin with a G1 approach to Z0 before the macro. Once done, the machine returns to G0x0 Z4. If unsure, repeat G0x0 to finish drilling. The bit size sets the measurement. If our path is not a multiple of 5, it doesn't matter. The last obstacle will be 2, 3, 4, 2.5 minute. It's not a problem. You see, as you can clearly see and understand, we start from Z4. For her, the pole is at Z4, so it will indeed take a first step to Z1, Z6, Z11, Z16, Z21, Z26, Z30. So the last step goes from 4 millimeter. Obviously I didn't optimize this. For example, you could have first set a simple G1 approach to Z0 and then started the macro. That said, once the macro is finished, the machine automatically returns to G0x0 Z4. If you're in doubt or have any concerns, just repeat G0x0 and you've drilled your hole, you've done your work. You see, in this very specific scenario, the machine doesn't care at all if you have a drill bit that's 1, 2, 10 or 20. It will make its hole, and then the size of the drill bit will determine the measurement. Also, especially in this case, the machine operates efficiently. If you're working with an insert bit for the machine, there's no problem. Insert bits are specifically designed for precision and efficiency, making them ideal for various machining tasks. If you need to make a 30mm hole, you have a 30mm bit for the machine, so working at 30mm is fine. This ensures that the hole is accurate and meets the required specifications. So if you have a zeroed insert bit, at this point, it can be used like a drill. This means that the bit is perfectly aligned and ready to perform the task without any adjustments. That said, with insert bits, it's not common to break the chip unless in extremely particular conditions. These conditions might include excessive force or incorrect usage, which are rare when proper procedures are followed. Now that we've made our hole, we need to thread it. Threading is an essential process that allows for the insertion of screws or bolts, providing a secure fit. So we have a hole that's 30mm deep, and we need to create a thread that's 20mm long, M14. What do we need to use in this case? We need to use a tap. For those who don't know, a tap, let me prepare a slide for this. Just look up M14 tap online, and you'll understand what it is. It's a cylindrical tool with a series of tapered threads, basically a male thread, which, when it goes in, removes material and creates the threading. This process is crucial for ensuring that the threads are clean and precise, allowing for a strong and reliable connection. It is obvious that when a tap enters, the mandrel must turn in one direction, as if it were being screwed in. When the tap reaches this position, the mandrel must stop. and turn backwards to allow the machine to go back without stripping the thread. Here's a little issue that CNC machines have solved for us quite easily. There are two methods for threading, with or without a compensator. What is the compensator? The compensator is a gadget that I personally hate. I've probably used it 3 times in my life. Basically, there's a sort of spring here, and when the tap reaches the bottom and the motion reverses, it allows the tap to oscillate in this way so it doesn't break, because during the reverse motion there's a real risk of the tap breaking. If you have the compensator, I don't know if you remember, you thread in G33, which means that threading is always done at fixed speeds, so it's called. The TO404 tool is typically written G97's 100 M3, or M4 if you're tapping right or left. This depends on the type of thread you're making. G0X0Z4, G33Z20F2, pay attention to M4. So, first, M4 S100 G1 Z4F2. I hope I wrote everything correctly because this isn't my usual way of threading, but I did take a couple of notes, so let's see if I got it right. Yes, perfect. These two blocks need to be written exactly together. So Z4F2. This is the right way to thread with the compensator. I've never seen anyone thread with a compensator in a company, so if there's anyone with different experiences, please write them in the comments because I'd love to hear them. If these compensators exist, there must be some applications or fields that go beyond my experience, and that's totally fine. So this is the method for threading with a compensator. I repeat, the compensator allows the tap to thread during the motion reversal, enabling an oscillation of the tap in this sense, so the motion reversal isn't a shock for the tool, and when turning in reverse it comes out like a screw. It was my duty to show you this. Now I'll show you the macro, the fixed cycle for rigid tapping. So the tap is locked in a chuck, which could be an R25 or R32 depending on the machine. This tap is secured in the chuck, and you don't move it in any direction from there. So the only thing you need to be careful about is to make sure that when you're at X0, the tap is perfectly centered with respect to the self-centering chuck. It was my duty to show you this. Now I'm going to show you the macro, the fixed cycle for rigid tapping. So the tap is locked in a chuck, which could be an R25 or R32, depending on the machine. This tap is secured in the chuck, and you don't move it in any direction from there. So the only thing you need to be careful about is to make sure that when you're at X0, the tap is perfectly centered with respect to the self-centering chuck. To know this, you position the machine with the 0 comparator on the self-centering probe on the shank of the tap. A 360-degree rotation gives you a range of 5/100ths. Otherwise, the tap is misaligned by a margin that risks breaking it. So, I repeat, when you're tapping, and even more so when you're drilling, check your machine. When you're at X0, the machine's X0 must align perfectly with the workpiece's X0. I warn you that this often does not happen in the company. Machine issues aren't from age or damage. Adjust X for 0. Shim if Y is off. Check X0 often, especially on older machines. Experienced workers know. So, as long as it's high in X and in X plus or X minus, you just need to move the XA. Little to make sure the probe's comparator is at 0 above and below, and tell the machine to measure X0, basically zeroing out the tap or the drill bit. However, when it's high on that hypothetical axis that we don't have, which is Y, you need to intervene mechanically on the tool holder's locking by shimming it. It's not nice to say, but shimming it makes people frown. In companies, we don't always have the latest machines in perfect condition. This isn't a check you need to do every time you mount the tap, especially if you're always using the same machine. You need to know your machine, so once every 4 to 5 setups, check that X0 corresponds. If it doesn't, make a note of it and write down any adjustments you made to bring it to 0, because this applies to all turret stations. Those who have been working in the workshop for a few years will definitely follow me. Those who have never worked in a workshop will remember my words one day and say, oh right, that guy from the course told me that despite everything the manufacturers say, I need to check the taps. Now, back to us. So, rigid tapping with alignment. Let's get back to it. So, rigid tapping with alignment. First of all, we need to force G97, telling it that we're working at fixed speeds, but we won't give it any data because the self-centering chuck shouldn't be rotating right now. I'm positioning myself at G0, X0, Z0. So first of all, we need to force G97, telling it that we're working at fixed speeds, but we're not giving it any data because the self-centering chuck shouldn't be rotating right now. I'm positioning myself at G0, X0, Z0. So I bring the tap right here. I remind you that the self-centering tool currently stopped. Give yourself a good margin in Z because you need to give the self-centering chuck time to start. When the chuck starts to move, it is also Z-axis. It will start moving, but it needs to accelerate. You can't go from 0 to F2 instantly. You need to go from 0 to F2 over a fraction of a second. If I haven't reached a constant speed by the time I enter the workpiece, I'll strip the thread. So it's better to start tapping well outside the piece. 2, 3, in this case, 4 times the thread. It's such a quick operation that time isn't our concern. It's about preserving the tap. At this point, I can't remember everything by heart. If I could remember everything, I'd be a pro. M29S150, M29S150, then G95, G84, Z20, F2. Now let's explain. G0, G80, approximately X200, Z200. We can place the M8 wherever we want. Tapping right is rarely done. So, what did we say to it? We are here. We brought ourselves here in front. M29, S150. M29, S150. We tell the machine, hey, watch out. We're starting a fixed cycle at 150 RPM. A fixed cycle for rigid tapping. Rigid tapping will happen in G95. If we've already set G95 earlier, there's no need to repeat it, but for sure, F is 2 millimeters per revolution. If I want to make a pitch of 2 every turn, my tap needs to advance by 2 millimeters of thread down to Z20, and then I'll come back. It already tells. There's G84 at the starting point, so the self-centering tool starts, accelerates, and when I find the hole, I'll already be at F2. I reach Z20, slowing down in such a way with an acceleration and deceleration that won't shock the tap, and then slowly the spindle turns in reverse, and the tap comes out. This is the rigid tapping cycle. G80 tells it to start the cycle. Finished. Move away. All rigid threads. are done this way. So for the M29 approach and the RPM, I want to thread, obviously. If I'm threading an M4, I'll have 300, 400 RPM depending on the quality of the tool I'll be using. If I'm threading an M20, I'll have 170, 180, again depending on whether I use a synthetic tap, an HSS tap, a taper tap, a Russian tap, or a German tap, because quality makes a difference. And then you need to make sure you're in G95, G84 with the feed rate equal to the pitch. If you have any doubts, use the thread pitch on the tap and check the tables. Never throw a tap with F2 into F1.5 because you'll break it or tear the thread. G80 says good, we're done, get out and go away. So any threading or tapping is done this way. This example has been brought to the simulator. In the simulator, we use tools T8 and T9. Excuse me. Here we go. To the tool offsets, T8 and T9. We set a radius for T8, which will be the drill bit of 6 mm, because it's a 12 mm bit, and the tap is an M14 with a radius of 7. After that, we told it that it's a bit oriented to position 2 and at 120 degrees, then a tap setting 2, and that's it. We don't need any more data. Here we just wrote exactly what we saw on the board. G97 S700 M3. We positioned ourselves, set the feed rate to G74 Z30 at Q5000, and entered all our data. The only thing we forgot is the M3 at this point, because we stopped the spindle. But let's take responsibility for that. So here we need to insert an M3. After that, we can execute. Here we have our GM29, G84, Z20. We can go. 29 G84 Z20, we can... I'm just asking the machine to actually simulate our part, and you can see that it's been done. Now it's not very clear, but here we have our piece. Let's pause, cut, and switch to a single block. You see, I started from Z2, I'm right at Z12, I move away, and now I'm at Z17, I move away, and let's indeed restart. I think it's a bit unclear. So now we're in single block, which means I'm doing one operation at a time. They are Z2, Z8, Z7. I'm breaking away from the famous R1, 8Z7, break from R1. Z13, Z12, move 13 to 18, 5 mm back to 17, complete hole, now 28. Need 30, go to 27, move 1 mm, last step, not from 5000, stops at 30, stop spindle, call tap, position front, roughing starts. Look, Z4, see it? Board had Z8. CNC adjusted, wrote Z4, moved back in Z to accelerate, then tapped. We didn't see it, but it tapped. You see it. Back to Z4. Notice, I move, stop the spindle, and start the roughing macro. The CNC adjusted from Z8 to Z4. For tapping, it tapped quickly and returned to Z4, showing its autonomy. We know how to turn, rough, drill, tap, and thread with G33. In the example on the board, I had already written Z8. The CNC, which is quite smart, automatically adjusted itself, even though I didn't write Z8 here but Z4. It moved back in Z by a distance that allowed it to accelerate on entry. Then it started tapping. We didn't even see it because it was faster than us, but it did tap. And you can see it from here. Okay, but look, it went back to Z4. Did you? Notice that it advanced. So there are some things that we programmers don't know. But the machine does them completely autonomously because it has parameters that say if I don't start from at least a certain distance, I can't tap. Perfect. Let's stop, restart, and do it all at once. I'd say we can wrap up this video here. So at this point, we know how to turn according to profiles, rough inside and outside, drill with the braking tool, tap, and we'll also know how to thread with G33, I read. We've seen the grooves, but now we're going to look at them together with the threading cycle, which is the famous G76 for making external threads with the turning tool, meaning not with the external or internal tap. It doesn't change anything. This is what we'll see in the upcoming videos. I'll try to rely more on the whiteboard than on the simulator, because this isn't a course focused on a single CNC. I want you to understand why we write these codes. If you find G170 instead of G84 on another CNC, it's just a code change. But the things a machine needs for tapping are the same: endpoint, safety distance, and pitch. So conceptually, nothing will change even if you switch CNCs. I thank you for being with me. I look forward to seeing you in the next video, and I wish you a good day. Bye everyone.